Saving energy, saving our future. Climate change is a global challenge we face today. One of the primary drivers comes from energy use. If we don't take action, we could face serious consequences like rising sea levels, droughts, and health issues. China is the world's largest energy consumer and a carbon emitter. Among all sectors, buildings accounts for nearly one-third of total energy use, and public buildings like hospitals, offices, and schools play an important role in that. To promote energy conservation, many smart technologies have been introduced. However, the effectiveness of smart controls can be undermined by insufficient user compliance. For example, in the setting of air conditioner operation. In summer, smart controls tend to set higher AC temperature to reduce energy use. However, this can make people uncomfortable if the temperature is too high, leading users to lower the temperature. Similar conflicts between sustainability goals and user preferences could also arise in other energy use scenarios. For instance, a driver's personal habit may not be environmentally friendly. So here's the key question we want to answer. How can we reduce energy use through smart controls while still ensuring that users are comfortable and willing to cooperate? We look into different smart control strategies and assess their impacts on energy savings and user compliance. Last summer, we carried out a randomized control trial in Hubei province, China. The experiment involved 20 public buildings. The idea behind smart control is that the controller checks the AC temperature at regular intervals. If it drops below a preset limit, the controller automatically adjusts it back up. Importantly, users can still use the remote at any time to override. This way, we can observe their behavior while minimizing their resistance, and data are sent to a centralized platform where control strategies are transmitted. On the platform, you first select the building, then choose the room. On the next page, you enter the temperature limit and how often the system should check. We designed 5 control strategies. First 3 groups from low to high had different temperature limits. Naturally, we expect that higher temperature limits will lead to more energy savings. Next, the high-frequent group has more frequent adjustments, every 15 minutes. Finally, we test a dynamic strategy where the temperature limits will be adjusted for selected samples based on users' past behavior. Basically, if the user seems satisfied, the limit will be increased by 1 Celsius degree. If the user seems dissatisfied, the limit will be decreased by 1 Celsius degree. Otherwise, it remains the same. We use difference in differences to estimate the effects. Smart control strategies show differential impacts on energy use. However, statistically significant energy savings, nearly 20%, were only observed in the last 2 groups. This implies that simply increasing the temperature limit isn't enough. More frequent or dynamic strategies can better unlock the full potential of smart controls. We also look at user behavior. The more often they adjusted the AC temperature, the lower their compliance. We find that as temperature limits increase, users are more likely to make adjustments. But under frequent and dynamic strategies, users actually did not resist more, which is encouraging to us. While you may wonder, did users feel comfortable or not? Our feedback survey shows that stricter strategies did not necessarily lead to higher dissatisfaction. To sum up, we provide empirical evidence for smart control as an effective energy-saving approach. We emphasize the importance of user compliance in green technology applications and offer practical solutions to resolve the tension between sustainability goals and user-centered considerations. Finally, we would like to acknowledge all our collaborators from Tsinghua University and Cornell University. Thank you for watching.